Okay, welcome to class. I'm Eric Admin, president of the Sno-King Watershed Council. In this class, physical chemical monitoring, we're going to learn about a particular type of water monitoring. So first, a little bit about the Sno-King Watershed Council. We are an all-volunteer nonprofit organization, and we help people protect local creeks and natural areas. We're also part of Global Water Watch. Global Water Watch is an organization which works around the world teaching volunteers to do community water monitoring. Global Water Watch has provided the training materials, methods, and database functions that we use. We're headquartered in Auburn, Alabama, and have a parallel organization, Alabama Water Watch. Because we use the same techniques as Alabama Water Watch, we also use some of Alabama Water Watch's training materials, including some demonstration videos that we'll watch as part of this class. So here's our agenda for today. We're going to learn about some common water quality variables and why they are monitored. We're going to learn Global Water Watch techniques for physical and chemical monitoring, answer any questions that you have, and talk about our upcoming practical training. So first, let's talk about some common water quality variables that are monitored. These are examples of variables that are monitored by King County that constitute something called the Water Quality Index. And it's a way of assessing the overall water quality by aggregating these variables. So we monitor many, but not all these variables, but these are all variables that are important for water quality. There's a variety of different ways that you can collect and process information depending upon your goals and on your resources. So you may use an electronic meter, or you may collect samples to be analyzed by a laboratory. You may use a fixed monitoring device that's at a fixed location, or you may do your analysis on site using a simple test kit, which is what we do. Each of these different methods has their pluses and minuses. So in terms of an electronic meter, cities, counties, some nonprofits use these. This is an example of one that we have that we use for certain applications. There's an electronic meter, and then there's a sensor probe that gets dropped in the stream. The plus side of these is that they're very precise and accurate, and they get you very rapid results. The downside is that they're very expensive. They typically cost several $1,000s a piece, and they need calibration, ongoing calibration before you go out. And because they're expensive, it's difficult to distribute them widely amongst a group of volunteers. This particular meter measures temperature, dissolved oxygen, total suspended solids, and conductivity, as well as nitrates. You can get different probes to measure different things with these types of meters. So this is the standard equipment that we use for water chemistry monitoring with Global Water Watch techniques. It consists primarily of a Lamont test kit, along with a few other items you need to monitor. And the other items include instructions, a clipboard, data sheets, bottled or tap water, a waste container for your reagents when you're done with your test reactions, pens and pencils, gloves, and hand sanitizer. The kit is organized into areas which correspond to each of the different types of tests that will be conducted. So for example, all the bottles and chemical reagents corresponding to the dissolved oxygen tests are in a location that's highlighted in yellow. And if you keep things organized in your kit the way that they come like this, it'll help you just quickly locate them when you're doing your tests in the field. So we're going to go over some basic principles that you want to follow when water chemistry monitoring. The first one is to have a set of written directions with you and to read and follow the steps carefully. If you forget a step, your test will not turn out right. And by the way, you may see a page number referenced on these slides, which refers to a page in the water monitoring manual, in case you want to look up any of these items. The tests in the Lamont kit use things that we refer to as reagents. Those are chemicals that are used in the test. This one is sulfuric acid. Each of these reagents has an expiration date. And so before you go out monitoring, you should look at the reagents in your kit and make sure they're not expired, because that can affect your test results as well. A couple other general principles. You want to record your results as you obtain them. So for instance, you may have done a test for hardness and you had to use 5 drops of hardness reagent to finish titrating that reaction. If you don't write it down when you obtain that result, you may forget. And so it's best to just write your results down on the data sheet as you go along. And then also enter your data online to the Global Water Watch site so that your data gets recorded. As a best practice, we don't dump out the reagents that we use at the stream, but we collect them and bring them back. They're sufficiently diluted and not generally hazardous, so they can go back in the drain at your home or office. And probably our most important general principle is that if you think you've skipped a step or done something wrong, do the test over. A saying that we use often is having no information is better than having wrong information. Another tip is that while you're doing your monitoring, it helps to keep things organized. And so you can use the kit itself as you do your tests to hold the bottles, the reagents, the tubes, so that they don't tip over, cause you to have to start your test over again. When you're filling tubes with water that you're going to sample, you're going to be asked to fill them to a certain level. And when you look in the tube, you'll see that the water surface makes a curve, and that curve and the bottom of the curve is referred to as the meniscus. So you want to be sure that that bottom of that curve, or the meniscus, is even with the line that you're trying to fill to. So in this case, we're filling that tube to 10 parts per million. We want to have the bottom of that curve at the 10 parts per million mark. And we'll show you a technique where if you've overfilled it, you can systematically get the level down. We call it the flicking technique, and you'll learn that. Another tip has to do with dispensing reagent drops. So when you're dispensing the reagent drops from the bottles, the first thing you're going to do is hold the bottle right side up, squeeze it, then turn it upside down and release it so that it draws in a little bit of air. Then you can dispense the drops. Otherwise, they may run out too quickly for you to count. So squeeze, invert, release is how you do the drops. Most of the tests that we do involve a concept called titration. And that means that you're adding drops of a reagent until you get a color change. You're done with the titration reaction when there is no more color change. So typically what you'll do is you will put in some reagents to get your initial color. Then you'll start titrating with a different reagent, and you're looking for a color change. So in this case, you can see it's going from a red, we're working towards kind of a blue. You get to the what you think is the end, and then you'll add another drop until you don't see any more color change. So for instance, if it took us 5 drops to get to that color on the very far right, and we add 1 more drop and we don't see any more color change, then we would record that as 5 drops. So we don't count the last drop. Let's talk about some of the specific tests that we conduct and some of the principles. So one of the tests that we monitor is, one of the variables that we monitor is temperature. And there's some important concepts about temperature. Temperature is one of the most important factors for things which live in the water for a number of reasons. One major factor is that cold water holds more dissolved oxygen than warm water does. Another factor to be aware of is that our test reactions happen more slowly in cold water, so you may have to give reactions a little bit more time when you're testing in cold water. And some of the key, what we call salmonids, which is salmon, trout, and steelhead that we have around here, really need cold water because they're very active fish and they need high dissolved oxygen. This is a table from Washington State Administrative Code guidelines for freshwater standards, and it shows you the temperature that's required for different types of salmon activities and habitat. Okay, some tips about monitoring. One is you want to hold the thermometer by the eyelet, not the bulb, when you're reading temperature. And the reason for that is that if you hold it by the bulb, which is down at the bottom, you can affect the reading. Another principle is that if you only have one thermometer, you want to measure air temperature before water temperature, because if you measure water temperature first, then what can happen is you can get some evaporative cooling that could affect your air temperature reading. And you're going to record temperature to the nearest 0.5 unit in Celsius. So what we're going to do right now is we're going to watch a demonstration video on air and water temperature.
Air temperature. Always take air temperature before water temperature for the most accurate readings. Upon arrival at your site, find a place in the shade where you can place, preferably hang, the dry thermometer. If you do not have shade, you can create shade with your body. Allow the thermometer to remain in the shade until the temperature stabilizes. This will usually take 2 to 3 minutes. To read the temperature, hold the thermometer by the eyelet at eye level. Remember, never touch the bulb of the thermometer, as you will end up measuring your body temperature instead of the air. Read and record the temperature to the nearest ½ degree Celsius on your data form. Once you finish measuring air temperature, you are ready to measure the water temperature. If possible, find a location that is shady and in the same area of the water body where you plan to collect your sample. Submerge the thermometer in the water about 2 to 3 inches. It may be necessary to anchor the thermometer to prevent loss in strong currents, cloudy water, or deep water. This can be done by tying a cord through the eyelet and attaching it to a stable object. If no such object is present, you can hold the thermometer in place. Try to avoid allowing the thermometer to rest on dark rocks, as it will affect the temperature reading. Leave the thermometer in the water for 2 to 3 minutes. Once the temperature stabilizes, read the thermometer while it is still submerged or immediately after removing it from the water. Record the temperature to the nearest ½ degree Celsius on your data form.
Okay, anybody have any questions on that? It's pretty straightforward. Okay, then we're going to continue along and we're going to talk about pH. So pH stands for percentage of hydrogen ions in solution. And in practice, it means how acidic or basic a solution is. The scale runs from 0 to 14. So on the lower end, it's acidic. 7 is considered to be neutral. And higher is basic. The optimum for fish is kind of in that neutral range, which is 6.6 to 8.5. So the way that we measure pH is there's a particular test tube that we use that you're going to rinse 3 times with sample water and fill it to the 10 ml line with sample water. Then you're going to add 10 drops of wide range indicator, cap it and invert it several times. It's going to turn a color. And then you compare it to a color chart in the so-called octaslide viewer and get the pH value to the nearest 0.5 unit. So pretty straightforward. So we're going to watch a short demonstration video on pH.
This video will show the proper method for collecting water samples and conducting the pH test. We will demonstrate how to test pH using both the OctaSlide viewer, which has been included in Lamont kits since 2013, and the color comparator from kits purchased before 2013. The methods used with each version of the test are relatively similar and produce credible results if conducted correctly. We will begin with the OctaSlide viewer. For this test, you will need a small plastic tube with a cap, code 0106, wide range indicator labeled WRIND, code 2218-G, and the OctaSlide viewer with OctaSlide color bars. Remove the small plastic tube from your kit and rinse 3 times with water from your site. Fill the tube with sample water. Hold the tube at eye level and flick out excess sample water until the bottom of the meniscus touches the 10 milliliter line. This is your 10 milliliter sample. Locate the wide range indicator bottle in your kit. This bottle has a built-in dropper, so uncap the reagent bottle and gently squeeze it in the upright position to let some air out. Then turn the bottle upside down while releasing the pressure. This creates a vacuum inside the bottle that allows for more control to dispense drops and avoid excessive dripping. When dispensing the reagent, take care to hold the dropper bottle vertically. This ensures uniform size drops. Add 10 drops to your sample. Cap and invert the tube. You can cap this tube completely because it is plastic and won't break. Invert 3 times to mix. You will see that the sample water turns a pastel color. Pick up the OctaSlide viewer and the 2 color bars. Notice that the color bars display values and colors typical of the pH scale from 3 to 10.5. To determine the pH of the water sample, insert the tube into the OctaSlide viewer. Insert one of the color bars. Use a blank background like a clear patch of sky or the back of your data form, and position yourself so light is behind you so that you can clearly see the color. And identify the colored panel on the color bar that best matches the color of the water in the tube. If there doesn't seem to be a good match, swap out the color bar. Once you determine the best color match, note the pH value represented on the color bar and record the pH to the nearest half unit on your data form.
So the next one that we're going to talk about is hardness. And so hardness is essentially a measure of the amount of calcium and magnesium ions in water. A certain amount of this is required for living organisms, and typically it comes from minerals in the earth. So usually the geology of an area is the primary determinant of the hardness, but it can also come from some man-made sources such as concrete. And it's typically expressed as equivalent milligrams of calcium carbonate in solution. One thing you may find is that low hardness can indicate a high level of stormwater. So essentially it's diluting the calcium and magnesium. All right, so now we're going to watch a video demonstrating how to measure hardness.
Total hardness. This video will show the proper method for collecting water samples and conducting a test to determine the total hardness of a water sample. When monitoring in coastal waters, conduct a salinity test first. If salinity is detected, do not perform the hardness test. For this test, you will need the hardness tube, code 4488, hardness reagent number 5, code 4483-E, hardness reagent 6 tablets in a blister pack, code 4484A-J, and hardness reagent 7, code 4487WT/H. Remove the hardness tube from your kit. Rinse the tube 3 times with water from the site you are sampling. Fill the tube with sample water. Hold the tube at eye level and flick out excess water until the bottom of the meniscus touches the 10 ppm line. This is your 10 parts per million, or ppm, sample. Locate hardness reagent number 5 bottle. This bottle has a built-in dropper, so uncap the reagent bottle. Gently squeeze it in the upright position to let some air out, and then turn the bottle upside down while releasing the pressure. When dispensing the reagent, take care to hold the bottle vertically. This ensures uniform size drops. Add 5 drops to your sample and gently swirl to mix. Locate the hardness reagent number 6 tablet blister pack. This reagent is in tablet form and is very soluble. Take care not to touch the tablet or allow any water to come into contact with the tablet prior to dispensing it into the hardness tube. Hold the blister pack with the foil facing down over the opening of the tube. Press on the opposite side of the blister pack to dispense a single tablet into the water sample in the tube. Carefully cap the tube with the large blue cap. You will only need to partially cap the tube. Pressing the cap down completely on the tube could cause the glass tube to break. Gently swirl the tube until the tablet dissolves. Typically, a pink color develops as the tablet dissolves. Next, we will titrate our sample using hardness reagent number 7. The hardness reagent number 7 bottle also has a built-in dropper, so uncap the reagent bottle, gently squeeze it in the upright position to let some air out, and then turn the bottle upside down while releasing the pressure to create the vacuum to give you more control over the drops. When dispensing the reagent, take care to hold the bottle vertically. We will count how many drops of hardness reagent number 7 it takes to cause the sample to change to a blue color and to stop changing color. In other words, we will reach the titration endpoint. Add 1 drop of hardness reagent number 7 at a time to the water sample in the tube. Gently swirl to mix between each drop. Be sure to allow time between drops for the color change to occur, especially during cold weather. You will need to know how many drops you add to your sample, so don't forget to count. You can keep the bottle in the vertical position throughout the test. Continue adding single drops of the reagent until the pink color changes to blue and the additions do not cause a color change. Once you think you've reached the titration endpoint, or the point where the color is no longer changing, add 1 more drop. Do not count the last drop if there is no color change after its addition. In some cases, the sample water will turn blue after the hardness number 6 tablet dissolves prior to titration. This could indicate that there is no measurable hardness. However, you will need to titrate to confirm that no color change will occur with the addition of hardness reagent number 7. If you add a single drop of hardness number 7 and no color change occurs, record 0 mg/L for total hardness on your data form. On the data form, record the number of drops it took to reach the titration endpoint. Also on the form, to calculate a total hardness value in milligrams per liter, Multiply by 10 the number of drops of hardness reagent number 7 used. Note that if total hardness routinely exceeds 200 milligrams per liter, conduct the test by filling the hardness tube to the lower line, 20 ppm, and multiply by 20 the number of drops of hardness reagent number 7 used.
Okay, so that is hardness. Typically that goes hand in hand with the next variable that we're going to talk about, which is alkalinity. And so they're kind of opposite sides of the same thing. So if you had calcium carbonate, the calcium ion is the hardness and the carbonate ion is the alkalinity. And what alkalinity contributes to water is buffering capacity or capability. So essentially what that means is it makes the water more resistant to changes in pH if it has a higher alkalinity. And so too low of an alkalinity is more susceptible to change. Higher is less susceptible to change. Typically, once again, this is generally due to natural processes, but you may find, for instance, we found an area that we're monitoring. One of the groups that we're working with monitors an area called Puget Creek over on the Duwamish watershed. And that's an area where there was a lot of concrete kiln dust deposited as a waste product throughout the area, kind of an industrial waste product. And what we found is that the hardness and alkalinity was a lot higher there than it is in some of our other sites. So we're going to watch a video on how to measure alkalinity.
This video will show the proper method for collecting water samples and conducting a test to determine the total alkalinity of a water sample. For this test, you will need the alkalinity test tube, code 0970S or 0289, BCG MR tablets in a blister pack, code 2311J, the plastic dropper, code 0352, and the alkalinity titration reagent B, code 4493PSH. Remove the alkalinity test tube from your kit. Rinse the tube 3 times with the water from the site you are sampling. Fill the tube with sample water. Hold the tube at eye level and flick out the excess sample water until the bottom of the meniscus touches the 10 milliliter line. This is your 10 milliliter sample. Locate the BCG MR tablet blister packs. Tablets are very soluble. Take extra care to not touch the tablet or allow any water to touch the tablet prior to dispensing it in the alkalinity tube. Hold the blister pack with the foil facing down over the opening of the tube. Press on the opposite side of the blister pack to dispense a single tablet into the water sample in the tube. Carefully cap the test tube with a large blue cap. You only need to partially cap the tube. Pressing the cap down completely on the tube could cause the glass tube to break. Gently swirl the tube until the tablet dissolves. A blue-green color will likely develop as the tablet dissolves. If a pink or pink-gray color develops after you have added the BCG MR tablets and before titration, it could indicate that there is no measurable alkalinity. You will need to titrate to confirm that no color change will occur. If you add a single drop of alkalinity titration reagent B to the sample and no change occurs, record 0 milligrams per liter for total alkalinity on your data form. Next, we will titrate the sample by adding alkalinity titration reagent B with the dropper with either an orange or black bulb. We will count how many drops of alkalinity titration reagent B it takes to change the color of the sample from blue to pink, and more specifically, for when the color stops changing or reaches the titration endpoint. To begin, fill the dropper with the reagent by squeezing the bulb, inserting the dropper into the reagent bottle, and releasing the bulb. Review the dropper to make sure there are no air bubbles. If air bubbles appear in the dropper, squeeze the bulb to empty the dropper and refill it. When dispensing the reagent, take care to hold the dropper vertically. This ensures uniform size drops. Add 1 drop of reagent at a time to the water sample in the tube. Gently swirl to mix between each drop. Be sure to allow time between drops for color change to occur, especially during cold weather. You will need to know how many drops you add to your sample, so don't forget to count. Continue adding single drops of the reagent until the blue-green color changes to pink and eventually no longer changes with any addition. Once you think you have reached this titration endpoint or the point where the color is no longer changing, add 1 more drop. Do not count the last drop if there is no color change after its addition. Record the number of drops it took to reach the titration endpoint on your data form. Also, to calculate a total alkalinity value in milligrams per liter, multiply the number of drops of alkalinity titration reagent B used by 5 and record this value on the data form.
Okay, the next variable that we measure that we're going to talk about is turbidity. And turbidity is a measure of the relative clarity of water. So higher turbidity means lower clarity. And turbidity can come from natural or human-caused sources. So this example, there was dirt that was running off a construction site and ending up in a creek, Little Swamp Creek in Kenmore, and caused it to become very turbid. So that's what an example of turbid water looks like. In streams, turbidity can cause harm for fish and other aquatic life. So for instance, it can bury salmon redds. So if you have high turbidity all the time, that can result in a lot of sediment on the bottom of a stream. And another side effect of turbidity is that turbidity, the dirt particles that are in that make the water appear turbid, provide attachment points for other pollutants such as metals and bacteria. So there's a couple different ways that turbidity is measured. Actually, there's a number of them. One is using turbidity tubes, and there's a couple different scales and a couple different techniques that we use. So what comes standard in our Global Water Watch kits is these turbidity tubes on the top right there, which measure in what are called JTUs, which are Jackson turbidity units. Another standard turbidity unit is what's called NTUs. And NTUs are a more contemporary measurement used by most regulatory agencies when they talk about turbidity. So if you called up the Department of Ecology and said, hey, I found 50 JTUs, they would say, what? But if you said I found 50 NTUs over background, they'd say, oh, that's terrible. Let's investigate. So just for measuring and tracking changes of turbidity over time, we do use the standard JTU test, which is easier to measure down to a lower level. But when we have higher turbidity situation that we might want to report, or you can do it regularly, but basically the NTU turbidity tube is more useful for higher levels of turbidity, and it only is accurate down to a level of 8 NTUs. You can measure it with either a meter or a turbidity tube. In our case, we use a turbidity tube that gives us a good idea of what the turbidity is. But if you needed a more precise measurement, you might use a meter. So the basic method is we use the tubes provided in the Global Water Watch Lamont kit. One of them is labeled C for control, one is labeled S for sample. And you're going to fill the sample tube with water from the stream. And the control water, you're going to fill with tap water or bottled water. Then you're going to look down through the tubes and compare. There's a black dot at the bottom of the tube. You're going to compare how fuzzy or opaque does that dot look at the bottom of each tube. And you'll then, assuming that the control one is a little bit more clear than the sample water, you're going to add measured amounts of standard turbidity reagent until the control one is more cloudy, and then you're going to record those number of additions. So we're going to watch a video now on how to measure turbidity.
Turbidity. This video will show the proper method for collecting water samples and conducting a test to determine the turbidity of a water body. For this test, you will need 2 turbidity columns, code 0835, standard turbidity reagent, code 7520-H, and a stirring rod. Locate the turbidity columns in your kit. If you are using your own kit, we recommend labeling one of the turbidity columns with an S for sample and the other with a C for control or a T for tap water. Rinse the S column 3 times with sample water from the water body. Then fill the column completely. Flick out excess water until the bottom of the meniscus is at the 50 milliliter line with sample water. Place the S column on a level surface, like in the center of your kit. Position yourself so that you can look down into the column through the opening, preferably from a distance of only about 6 inches. You should see a black dot on the bottom of the column. If the black dot on the bottom of the column is not visible when looking down through the column, find the clear stirring rod and stir the water sample in the column. Flick out excess water until the bottom of the meniscus is at the 25 milliliter line with your water sample. Look down into the column to find if, with that sample volume, you can see the black dot on the bottom of the column. When successfully seeing the black dot on the S column, rinse 3 times your second column, the one labeled C for control or T for tap water. Fill the second turbidity column with the same amount of bottled, distilled, or tap water. Place the columns side by side with the column bases almost touching. Make sure that they are on a level surface, like in the center of your kit. Position yourself so that you can look down into the columns through the openings, preferably from a distance of about 6 inches. This time, you should see a black dot on the bottom of both columns. For this test, you will be comparing the clarity or the fuzziness of the black dots in the bottom of the 2 columns. Do not consider the color of the water. Typically, the tap water in the T column will be clearer than the sample water. Therefore, the dot at the bottom of the T column will appear clearer, sharper, with less fuzziness. We will determine the turbidity of our sample water in the Jackson turbidity units by counting how many additions of standard turbidity it takes to make the tap water have the same level of turbidity as the sample water. To start, find the standard turbidity reagent and the dropper that is marked at the 0.5 milliliter line. Shake the reagent vigorously, and then fill the dropper with 0.5 ml of the reagent. To do so, hold the dropper vertically. Squeeze the bulb and then insert the dropper into the reagent bottle and release the bulb. The dropper should fill with no air bubbles. If air bubbles get into the dropper, squeeze the bulb to empty the dropper and refill it. Hold the dropper at eye level and carefully squeeze the bulb and expel excess reagent to the desired sample volume marked 0.5 ml. Find the clear stirring rod and stir both columns. Tap off excess water between columns to prevent contamination. We recommend that you hold onto the foot of each column when stirring to prevent spills. Look down at the black dots at the bottom of the columns. If the T column is clearer than the S column, you will need to add the entire 0.5 milliliter of the reagent in the dropper to the T column. Make sure you dispense all the reagent in the dropper. Using the stirring rod, stir both columns, then look at the dots again. If the dot at the bottom of the T column is less fuzzy than the dot at the bottom of the S column, shake the standard turbidity reagent and collect another 0.5 milliliters in the dropper. Add the entire 0.5 milliliter to the T column. Stir both columns and observe the black dots. Continue this process of adding 0.5 milliliters of the reagent to the T column until the dots in both columns appear to have the same fuzziness or clarity. You will need to know how many additions you add to the control column, so don't forget to count. Once you feel the dots at the bottom of the T and S column have the same clarity, or in other words that you have reached the titration endpoint, add one more 0.5 milliliter addition. If the last addition causes the dot at the bottom of the T column to be fuzzier than the S column, it confirms that the previous addition was the endpoint. Record the number of the 0.5 milliliter additions you added to the control, not counting the last addition. You will notice on your datasheet that to calculate turbidity in JTUs, you need to multiply the number of additions by 5 if using a 50 milliliter sample. On your data form, you will notice that you also have the option of multiplying by 10 if using a 25 milliliter sample. In some rare cases, it is possible that the dot at the bottom of the S column is still not visible after reducing the volume to 25 milliliters. If this happens, record the turbidity as THTM, or too high to measure, in the comment section of your data form. In some cases, your 50 milliliter water sample might be so clear that the dots at the bottom of T and S columns are equal before adding the standard turbidity reagent. In this case, you should still add one addition of 0.5 milliliters to confirm that this is the case. If the T column is fuzzier than the sample after one addition, you should not count the addition. On your data form, report the number of measured additions as 0 and report JTUs equal 2. This is because it is very unlikely for a natural water body to have 0 turbidity. Also, the detection level for turbidity that is possible with this test is limited. Thus, reporting 2 JTUs for a 0 reading compensates for this fact.
As I mentioned, there's a NTU tube, turbidity tube, that we use as well. It's a bigger tube. And the way that you do this is you gather a sample of water, either by filling that tube or in a separate container. And you're going to fill the tube all the way to the top with that water. And then you release it until you can just barely see the disc, which is in the bottom of the tube. So if you look down through the top of the tube, you see this disc called a Secchi disc. And then what you'll do is compare the level in centimeters on the tube to a chart, which is on the tube, and it will give you the NTU reading. So it's pretty straightforward. And then you'll record that under the other observations on your data sheet. Now we also have a separate tube that's similar, but we call it a direct read tube. Basically, very straightforward to use this one. You fill it all the way to the top. You look down, and if you can already see the Secchi disc, then you essentially know that this tube is only going to give you, it's not going to give you measurable turbidity. But if you can't, you'll let water out until you can just see the Secchi disc, and then you'll read the number. And so if you look at the marks on that tube, the graduated marks that look like a ruler are centimeters, but then there's a chart that goes up parallel to that lists NTUs. So at the bottom, it's greater than 250, 240, 185, and 150 in that example in the picture. Okay, moving on to the final test that we do, which is for dissolved oxygen. So dissolved oxygen is important for a number of things. I guess it's necessary for animals, other creatures that live in the water, and plants create it. So basically there's two ways: either aeration, so like going over a waterfall, or caused by plants releasing oxygen. So depending on where you're sampling, those are some of the main sources of dissolved oxygen. There's a scale for different types of creatures that need different levels of dissolved oxygen. And so typically fish that are more adapted to warmer water are used to a lower level of dissolved oxygen, and so they can tolerate that. But trout and other salmonids that are adapted to cold water need a higher level of dissolved oxygen. There's also a relationship in terms of dissolved oxygen between temperature and dissolved oxygen. So there's an inverse relationship. So essentially, as dissolved oxygen, or as temperature goes up, the level of dissolved oxygen possible goes down, and vice versa. So cold water holds more dissolved oxygen. The basic process of sampling for dissolved oxygen is essentially 3 parts. Part 1 is collecting the sample. Part 2 is a series of titration reactions that fix the sample. And then part 3 is titrating the sample. And so titrating the sample, you're going to essentially add some reagents that will cause it to turn a certain color, and then you'll be titrating it with sodium thiosulfate until it turns clear. So we're going to watch some videos right now that show each of these different steps.
Dissolved oxygen. This video will show the proper method for collecting water samples to conduct a test to determine the average dissolved oxygen of a water sample. Step A, collecting the sample. To begin this portion of the test, you will need to locate the 2 water sampling bottles, code 0688/DO, in your test kit.
Make sure there are cones in the cap of each bottle.
You will use the water sample bottles in your kit to collect 2 replicate water samples at the same time and place in the water body. Collecting 2 replicate samples, also referred to as reps, ensures precision. To begin, rinse both bottles 3 times with sample water. To fill the bottles, it is necessary to hold both sample bottles in the same hand. This ensures that you are collecting replicate samples at the same place and time. Completely submerge the capped bottles under the water so that they are in an upright position that will allow the bottles to fill with water while all air bubbles escape. Avoid disturbing the substrate or stream bottom at the sampling site. Allow the bottles to fill completely underwater. Once bubbles have stopped emerging from the bottles, move or shake the submerged bottles to allow any additional air bubbles to escape. Do the same with the caps to make sure that there are no air bubbles in the caps. Replace the caps on the bottles while they are still submerged. Remove the capped bottles from the water and invert them to make sure that no air bubbles are trapped inside. If air bubbles are present, even if they're only in one bottle, empty both sample bottles and refill them with water again. Once a satisfactory sample has been collected, proceed immediately with the next steps. Step B, fixing the sample. This video will show the proper method for fixing the water samples so that you can complete the test and determine the average dissolved oxygen of the water sample. For this step, you will need manganese sulfate, code 4167-G, alkaline potassium iodide azide, code 7166/G, 1:1 sulfuric acid, code 6141-WT/G. Note that each of these reagents are considered hazardous substances. Take precautions not to splash the chemicals into your eyes. If you get reagent on your skin, rinse with water. Youth using these chemicals should be carefully supervised. Make yourself aware of and adhere to the recommended 4-H AWW safety protocols. Safety glasses, and in some cases gloves, may be required by some schools for student monitors. Before you get started, make sure you position the sample bottles on a level surface. This may be difficult streamside, so we recommend that you keep them in your kit, using your kit as a lab table. This will prevent spills and protect your hands from chemicals. We will begin by adding manganese sulfate to both of the sample bottles. The reagent bottle has a built-in dropper.
So remember to create a vacuum and hold the bottle vertically.
Uncap both sample bottles and add 8 drops of manganese sulfate to each sample bottle. Then, in the same way, add 8 drops of alkaline potassium iodide azide to each sample bottle. It is likely that the bottle will overflow as you add the reagents. This is okay and will not damage the kit. Cap bottles securely and rinse them in the water to remove traces of reagents that may be on the surface of the bottles. Mix the bottles by inverting them at least 10 times. At this point, a tan, cloudy precipitate will form. Allow the cloudy precipitate to settle below the shoulder of the bottles. Now, uncap the bottles again and add 8 drops of sulfuric acid, 1:1 to each sample bottle. Cap bottles and rinse. Repeatedly invert the sample bottles to mix until most of the dark brown flecks have dissolved. Be patient during this step. Brown flecks in DO bottles may take several minutes to dissolve, especially in cold water. Turbid water samples may contain fine particulate organic matter that may not completely dissolve. The flecks tend to be a more uniform size, shape, and color than the particulate organic matter. At this point, your samples are now fixed. This means the oxygen in the sample is chemically trapped and that contact between the water sample and the atmosphere will not affect the test result. Monitors have the option of holding or transporting fixed samples for up to 2 hours before further analysis. This is rarely necessary, but may be useful in some cases, including the occurrence of a storm that might prevent a monitor from completing the test stream side. C, titrating the sample. This video will show the proper method for titrating water samples as part of the dissolved oxygen test. For this step, you will need titration tube code 0608 or 0299, starch indicator code 4170WT/G, direct reading titrator code 0377, and sodium thiosulfate code 4169-H. This entire process should be completed for 1 sample bottle before starting the second sample. Rinse the titration tube 3 times with a small amount of the fixed sample from the first sample bottle. Be careful not to use too much of your sample so that you are sure you have enough to conduct the test. Pour the waste into a waste container or broadcast it over a vegetated area. Fill the titration tube to the 20 milliliter line with fixed sample water from the sample bottle. If you overfill, you can carefully flick the excess sample water into the waste bucket or onto vegetation so that the bottom of the meniscus is touching the 20 milliliter line. Remember, the sample contains caustic reagents, so use caution. Now add 8 drops of starch indicator to the tube and cap with the titration tube cap, which has a hole in the center. Gently swirl to mix. The sample should turn dark blue to black. You will need to fill the direct reading titrator with sodium thiosulfate by depressing the titrator and placing it into the hole in the top of the sodium thiosulfate reagent bottle. Invert both the bottle and titrator and draw out the titrant until the large ring on the plunger is opposite the 0 line on the scale. Make sure that there are no air bubbles in the titrator. If there are bubbles, you can push the sodium thiosulfate back into the bottle and refill. Keep the bottle inverted throughout this process. Sometimes you may need to do this several times to eliminate the bubbles. Next, insert the filled titrator into the center hole of the titration tube cap. Add 1 drop at a time of the sodium thiosulfate into the titration tube. Gently swirl the tube between drops. You do not need to count the drops for this test. Continue titrating by adding more drops one at a time until the dark blue or black solution turns completely clear. Hold the tube against a white background to be sure that the solution is clear and not faint blue. Note that it may take more time for the color change to occur during cold weather. Once the solution is clear, read the number on the titrator where the whitest part of the plunger meets the line on the scale. Each minor division on the titrator scale equals 0.2 ppm or parts per million. Record the value to the nearest 0.2 ppm on your data form for rep number 1. If the plunger tip reaches the bottom line on the titrator scale, or 10 ppm, before you have reached the titration endpoint, refill the titrator to the 0 line with additional sodium thiosulfate and continue the titration. To determine the oxygen concentration, add the original 10 ppm to the second ppm value and record the total value. Repeat the procedures of this step for the second sample bottle and record the results for rep 2 on the data form. If the DO results for rep 1 and rep 2 are not within 0.6 ppm of each other, repeat the steps for titrating the fixed sample in the first bottle. If results still vary by more than 0.6 ppm, repeat the steps for titrating with the sample in the second bottle. If there are still not two results within 0.6 ppm of one another, you will need to repeat the entire test by beginning with sample collection. Leftover titrant or sodium thiosulfate in the titrator could have been contaminated with the water sample and should be discarded. Do not return leftover titrant to the bottle. As you can see, the dissolved oxygen test has many steps, and at times you have to wait for reactions to take place between the steps. For this reason, many volunteers like to begin with the dissolved oxygen test so that they can move on to the other tests while waiting for DO reactions to complete.
So the final thing that we do with dissolved oxygen is we calculate a saturation. And so essentially, we compare what was the number that we came up with for dissolved oxygen for what the maximum number would be at that same temperature. And we use a chart to compare that and then do a little bit of math to just say, okay, so let's say that we were measuring at 10 degrees Celsius and the maximum predicted would be 11.27, but we got 10. So we divide 10 by 11.27 to come up with percent saturation. And that's something that you can do and enter on your chart, or when you do the online data entry, that part is done for you. So the implication of DO saturation is essentially you just want to find that it's in an acceptable range. So in some cases it can be too high. That's pretty rare. That might be like something you might find at the bottom of a dam where there's a tremendous amount of aeration happening, or you could find very warm water that doesn't have very much dissolved oxygen. But generally speaking, usually we find that it's within an acceptable result. So then you just finish recording your results on the monitoring form, input your information to the Global Water Watch database, and that's it. You have completed your water monitoring. So as usual, thank you to all those individuals and organizations that have helped us make this program possible. And with that, I'm going to stop the recording and I'll take any questions and we'll talk about our upcoming practical training.